Hello, my name is Isaac Esquivel, and today I'm going to be talking about Lewis structures. Now, Lewis structures are simple models that allow us to look at how atoms bond together. So, atoms do their bonding through electrons, and specifically valence electrons, which are the outermost shell electrons. We can actually find out how many valence electrons are in an atom by looking at their group number. Now, we're going to be specifically looking at the A groups on the periodic table, and there's 8 of them. So all the way on the left of the periodic table, we have our groups 1A and 2A. We'll find hydrogen and beryllium under them. And then if we go all the way on the right side of our periodic table, our 3A group starts with boron and continues on. Now, to determine the number of valence electrons in any atom under these groups, we simply look at the group number, and that would be the number of valence electrons. For example, carbon, which is in group 4A, has 4 valence electrons. Oxygen has 6 valence electrons. Chlorine has 7 valence electrons. The only exception to this would be helium, which only has 2 valence electrons, but any other atom underneath group 8A would have 8 valence electrons. So let's draw a few atoms, a few Lewis structures of atoms to look at their valence electrons. So for a Lewis structure, we start off with a symbol, an atomic symbol, to represent the nucleus of the atom and its inner shell electrons. And to draw our valence electrons are represented by small dots. So carbon, which is in group 4A, has 4 valence electrons. Oxygen, which is in group 6A, will have 6 valence electrons. So drawing Lewis structures is as simple as that. When forming bonds, atoms seek to fulfill what is called the octet rule. That is, they seek to have 8 valence electrons in their shell. There are a few exceptions to this, one of which is hydrogen, which can only have up to 2 electrons in its outermost shell. So let's look at some bonding of a few atoms, a few molecules. Let's start with F2. So the first step that we're going to take in determining the Lewis structure of F2 is to determine the number of valence electrons, total number of valence electrons in the molecule. So I have 7 valence electrons for fluorine because it's in group 7A. We'll multiply that by 2 since there are 2 fluorines. So we get a total of 14 valence electrons. So the first thing we're going to do is the next thing we're going to do is draw our our molecule structure, which is fairly simple for this as it's just 2 fluorine atoms. We'll put a pair of valence electrons between the 2 atoms to represent a bond between the atoms. And so we've now used 2 of our 14 valence electrons, which means we have 12 left. And we could just fill these in by putting them around the fluorines. And there you have 14 valence electrons. And you'll notice that the octet rule is satisfied for both fluorines. You have 8 for this one and 8 for this one. Both of them share this pair of electrons in the middle, forming the bond. Let's look at O2. Each oxygen has 6 valence electrons, so we're going to have 12 valence electrons in O2. So again, we start by drawing our bond between our oxygens, and we have 10 valence electrons to fill in. Okay, so there's our 10 valence electrons, but you'll notice right away that this oxygen only has 6 electrons in its outer shell. So we can take a lone pair from the other oxygen and make another bond. Now we can count we could count the 4 electrons in the bonds for each oxygen atom. So you can see this one has 8 valence electrons, and this one has 8 valence electrons. Another way we could represent Lewis structures is by drawing lines in between the atoms to represent bonds. Each line represents 2 valence electrons, so you can see right here we have 2, 4, 6, 8, 10, 12. Let's look at N2, which has 10 valence electrons. That's 5 for each. We have 5 for each nitrogen. So right here we have 10 valence electrons. However, this nitrogen only has 4 valence electrons. So we could take 2 pairs of electrons and form 2 more bonds. Right here we have a triple bond between the 2 nitrogen atoms. This is the maximum number of bonds that can occur between 2 atoms. Let's look at some more complicated molecules. CH2O, formaldehyde. So our first step, again, is to determine the number of valence electrons. So we have 12 valence electrons, 4 coming from the carbon, 1 from each hydrogen, and 6 from the oxygen. So our next step is to determine the structure of our Lewis, the backbone of our Lewis structure. And so generally, when we have a carbon molecule, we will use the carbon as the central atom and draw the other atoms bonded around it. Okay, so we've used 6 of our 12 valence electrons, so we have to put in 6 more. Notice that we cannot put any around the hydrogens, as they can only have a maximum of 2. Now right here, you'll see that our oxygen is lacking 2 valence electrons. So let's form a double bond. And there is the correct structure for formaldehyde. Next, let's look at CH2O2. So again, let's start by counting the valence electrons. So we have 12, 16, 18. 18 valence electrons. So let's do like we did last time and start with this carbon atom as the central atom and put the other atoms around it. Right here we have 2, 4, 6, 8, 10, 12, 14, 16, 18 valence electrons. We've used up all of our valence electrons, and notice that our oxygen is still lacking 2 electrons. There are no lone pairs on the carbon that we can take to put into a double bond. We do have lone pairs on this oxygen. However, if we took those, then that would leave this oxygen deficient. of 2 electrons as well. So what we could do is we could take one of the hydrogens and its electrons and bond it to the oxygen. Now notice that our carbon is now left with only 6 valence electrons. So again, simply take a pair from the oxygen and form another bond. And this would be the correct structure, Lewis structure for this molecule. Finally, let's look at CH4O. So number of valence electrons, we have 4. 14 valence electrons total. Now notice that if we use the carbon as our central atom, we cannot put all 5 molecules around it, as carbon can only form a maximum of 4 bonds. So let's start by bonding the carbon and the oxygen together. And we can add the hydrogens around the carbon and the oxygen. You can add either 3 to the oxygen, 1 to the carbon, 3 to the carbon, 1 to the oxygen, or 2 each. So let's start by adding 2 to each. Two, 4, 6, 8, 10, 12, 14. So all of our valence electrons are filled in, and the molecule looks like it's pretty stable. The octet rule is completely filled. However, it could also take the form of this. So how will we know which one is more stable? Well, we can use something that we call formal charge and allot the electron charge to each individual atom. So let's start by looking at the carbon in here. And the way we do formal charge is we first take the normal number of valence electrons. So normally carbon will have 4 valence electrons. And then we count 1 electron from each bonding pair and 2 for each lone pair. And we subtract that from the normal number of valence electrons. We have 5. 1, 2, 3, 4, 5. Giving us a formal charge of -1. If we look at the oxygen, we also have 5. However, oxygen normally has 6. So the oxygen will have a formal charge of +1. Now let's look at this structure. Let's look at the carbon. Carbon normally has 4. Let's count the number of electrons for the formal charge. Notice that we only have 4 right here, so that we get a formal charge of 0. I'm sorry, I forgot to put in the rest of the valence electrons for that. Oxygen normally has 6. Right here, since we have 2 lone pairs, we count 6 electrons. So in this structure, carbon and oxygen each have a formal charge of 0. So we know that this structure is more stable. And that's it on Lewis structures.